One thing about it is, well, a few things about it. This is what you'll get for your next unit exam. Okay? So, you'll, you don't have to bring it, I'll bring it. But already does, hopefully, based upon what we talked about Friday when we met, some of this is like, oh, well, that's first order test, or that's zero order test, or that's second order test, and that's one thing you can be responsible for. Actually, along those lines, we are going to use these integrated time concentration equations now to do some problems. Okay. So we said, you know, you can use the integrated time concentration equations to come up with 3 plots to test for zero, first, and second order. And we're going to take that a little bit further then. Why not? Reaction orders. You can only get to them using experimental data. So why would we use these integrated time concentration equations? Well, one is that you can calculate the time needed to get to a certain concentration, okay, because those equations link T time, initial concentration A sub 0, molar concentration at time T, that's just your A. Or you can calculate the concentration after a specific amount of time. Calculate A after time T. Okay, so it's all about plugging and chugging, but I wish it were that easy. Okay. There she is. Hey, Benny. So I actually, and you can if you want to, I'm going to find this on my equation sheet, and I am going to write first order next to it because I am bad about remembering which is zero order test, first order test, second order test. Okay. Where did all my pins go? So here we go. First order, dun 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 dun. The natural log of the ratio of A to A naught is equal to negative KT. And this actually is also first order, so I'm going to find this one on there. Is this one on there? The ratio of, maybe this one isn't on there. You should be able to, actually the last one is kind of like this, where if I take that one, the ratio of A to A naught is equal to E raised to negative KT. First order. What else we got? Second order. Got this one down here. Actually, both of these are second order. Actually, all three of these are first order. Oh, this is very easy. So these three are first order. These two are second order. And again, you can't take this, bring this with you to your test, but I'll try to make sure it looks pretty much like this. This first one, I'm like in zero order. I would do. When you did your homework for that's due today, that was you plotted along the y-axis, you plotted the molar concentration of A. On the x-axis, you plotted the time, and your slope is negative. It goes straight to the order. Okay. All right. Zero order test?
Yeah, the
integrated time concentration equation? All right, so let's just jump in there and do an example. So the fact that this says it's first order, the reason I belabored that is because now I know which equations I can use. I'm going to kind of pull information out from here. The information I get is given first order. You're going to see me take, I don't want to say the molar concentration of antibiotic all over the place, so I'm going to actually call the molar concentration of A is equal to the molar concentration of antibiotic. Okay, it gives us the rate constant. We good with that? 1.65 per year, that's K. This is K. Okay, all right, what else are we given? It says if an initial concentration of antibiotic, 0.0060 molar, is stored at 20 degrees Celsius, so this is my A0. This is my A0, this is my K. Where's my little marker thing? This is K, this is A0. Okay, what will be its concentration after 3 months? Here, 3 months, that's T, time. A follow-up question is how long will it take for the concentration to be equal to 0.0010 molar? So that would be this. Okay? So we've got some stuff here. We should feel pretty darn good. You have these in your hot little hands and you know it's first order. So like I said, I don't want to write the word antibiotic like 10 million times, so I'm going to go ahead and define anytime you see the molar concentration A, that is the molar concentration of antibiotic. So we know for first order we have this relationship. The concentration at time T divided by the initial concentration is equal to E raised to the negative KT. And actually I'm going to use this one. You're like, now which one do I use? Well, this would be a good one. If I have T, if I have time, I could rearrange this to get to A, and it looks like this. Just rearranging it, people. Like how this is the form you see on the sheet. So at any time T, the molar concentration is the initial concentration times E raised to negative KT. K was given in the original problem, and time was what, 3 months, okay? Don't make it harder than it is. I'm gonna have to fix my time, aren't I? Because my K is not in units of time. My K is actually in units of per year. So I'm either gonna have to fix my months to years or my years to months. I can't remember which one I did. Okay. So it's kind of like the gas laws. We're gonna plug and jug. Plug and jug, people. Looks like I'm gonna fix my time from 3 months into years, a fraction of a year. Don't forget to show all of your work. 3 months times 1 year for 12 months. So that's 3 divided by 12, which is 0.250. 3 sig figs. That's my T. And that's what I'll plug in right in here. Now, you're going to want to run these through your calculator physically because you'll run in, how do I say it? You'll need to be able to do on the test, and you'll need to be able to use this E raised to a power sort of thing. All right, so it looks like this, substituting in. We have the molar concentration at time T is equal to the initial molar concentration, 0.0060 moles per liter, times E raised to the negative KT. K was 1.65 per year, and T was 0.25 years. Notice units of years cancel, which is great. You should come up with a nice, round, beautiful number. Round to 2 sig figs, you're looking at, given that time, your molar concentration will be 0.0040. Everybody's kind of digging out their calculators. I think I have the calculator here. So my E key is a shift in my LN. So should work. So I'm going to go shift. And I'm going to begin parentheses. Oh, I'll put negative. Begin parentheses. 1.65 times 0.25 end parentheses, and I'll multiply that by 0.006. Okay? Looks good to me. All right, so that's the answer to the first question, first order, because we know it's first order. Now this one, we know it's first order, but we're going to use this version of our first order integrated time concentration equations because we're trying to solve for time, and it's hard to solve for time when it's an exponent like that. We can take the natural log of, which is what we're doing here. But this version says that the natural log of the ratio of what you have at time t to what you started out with is equal to negative kt. Rearrange that, solving for time. Time then is equal to the inverse of the rate log constant k times the natural log of the ratio of a to a0. So, in this case, of course, we still have the initial concentration of A, and K is the same. Our target concentration of A is to decrease to 0.0010 moles per liter. So, plugging and chugging. The time then is equal to the inverse of negative 1.65 reciprocal years, which again, we have the reciprocal years in the denominator. That's actually years, normal years in the numerator, times the natural log of the ratio of A to A0. And A, our target concentration we're after, time in question, 0.0010 moles per liter. Our initial molar concentration, 0.0060. Now I have a slide to kind of point this out, but let's see if this works for you. Actually, do you see where in this form, how do I say this? This actually, it could have been given as a percent remaining. It would have been, it's the same thing. The ratio of what you have left to what you started out with is the same thing as the percent remaining. So anyway, rounding it to 2 sig figs. Oh, so I'm giving myself 3 here. I'm not sure why, but we'll go with it. Rounding to 3 sig figs, you're looking at 1.09 years. Okay, so that's the answer to those 2 questions using the first order integrated time concentration equations. Again, which one you use depends upon what you're after. Let's do another one. Butadiene actually goes ahead, takes 2 of those, and to make the C4H6 to make 1 C8H12. It's second order, so we've switched gears. We're going to go with these guys now and answer a few questions. Again, the K is given. Okay, so it's overall second order, so these units make sense, liters per mole per hour. The 2 questions look like this. Well,
so, how do you know right away when it's second order?
Because it was given. I told you.
Oh, by second order. Oh.
Yep. It has to tell you,
Okay.
or, and actually I have a slide to kind of point this out. We could have known it was second order since it was overall from the units.
Okay.
So sometimes from the units you can backtrack. Units of K, excuse me. So our A0 is going to be 0.020. We have our A0, we have our K. Let's look at the questions we could run into. So first off is given T is equal to 1 hour. What's A? And the other one is given A, let's see, given A is 0.0020, what's T? And I pause because you have to make sure you are reading the problem correctly. And this says that actually the molar concentration is decreased to this. If it said the molar concentration decreased this amount, you have to do the subtraction to come up with your A. I don't know if that makes sense. But make sure you read it carefully. Okay. So again, we're going to go ahead and state anytime you see A or A0, that's the reactant, the C4H6. So with that in mind, we're going to, our first one is we were given time and we're after the A. So what I would do is just leave the inverse of A by itself. I wouldn't try to flip it over or anything crazy like that. So it looks like this. I'm going to leave the inverse of A, and at the end I'm going to flip it. So rearranging this, I can say inverse of A is equal to KT plus 1 over A0. And I have T, I have K, and I have A0. So here we go. The inverse of A is equal to K, which is 144, don't forget your units, liters per mole per hour. The time was also in units of hours, we didn't have to fix that, 1 hour. So now we know that units of hours are going to cancel with this first term, and we're going to be left with liters per mole. The second term is simply the inverse of the molar concentration, the inverse of the initial molar concentration, so the inverse of 0.0200 moles per liter. Again, with these units, that's the same thing as units of liters per mole. So bottom line, I'm going to get units of inverse of molar concentration of A is going to be units of liters per mole, which is perfect. Do the math, and you're actually going to come up with a number of 194. We're not done yet, though. That's 194 liters per mole. So if we want moles per liter, we have to go ahead and take the inverse of that. So in other words, to go from the bottom, from the left, 194 to the 0.00515, this actually is 1 over 194 to get this number. So we have to unflip it. And we unflip it or flip it, I don't know what to say, flip it one more time. That's going to leave us units of moles per liter, which is molarity. Doesn't hurt to say, does this seem reasonable? We started with 0.0200, and now we're at 0.000515. At least it went down. It's in the right direction. It's not bad once you have the equations. Aren't you glad you get to have the equations? Yes, me too. Makes my life easier. Okay, so for the second one, we are given time. For the second one, we're trying to find time. So we can rearrange this, and we can say that the time will be equal to quantity, the inverse of the rate law constant K, times quantity, the inverse of A minus the inverse of A0. Just rearranging it. But it never hurts to take your time. Make sure you get it right. So these are the numbers we're going to plug in. The concentration of interest is 0.0020 moles per liter. We're just going to see how long it's going to take to get that new concentration. So we have the inverse of K, so 1 over 144 liters per mole per hour times this difference here, the inverse of A minus the inverse of A0. And those look like I'm looking at the same number, but they aren't. Inverse of 0.0020 moles per liter minus inverse of 0.0200 moles per liter. And if you're like me, you don't do a lot of these sort of types of inverse things. But oftentimes, calculators will have an inverse key, x to the minus 1. You might find that handy. So rounded to, I think 2 sig figs. Did I give myself 3? Yeah, only 2 sig figs. You're going to have the value of 3.1 in units will be hours, because you figure the first term is liters per mole in the bottom, and the second term is moles per liter in the bottom, and they basically, those annihilate each other. Also in the denominator of the rate law constant K, we also have inverse hours, which is the only unit that doesn't get annihilated. The answer, second order kinetics. So there's this thing, and you're going to see it here in a minute. It's half-life. Half-life is the variable the time it takes to get 1/2 of your stuff used up. Half-lives, of course, vary, depend upon reaction order. So by definition, a half-life is when the molar concentration that you have at time t is 1/2 of your initial concentration. Makes sense? So we can actually take, this is right. we can actually take that information and plug it into our integrated time concentration equations. And it looks like this. If we go for the first order, what we're going to do is take this concentration A, and we're going to make it 1/2 of A0, and we're going to make that T is going to be the half-life. Go ahead and do some substitutions. Okay, so this is just for first order reaction kinetics of our reactant A. So things kind of fall into place. Notice 1/2 A0 over A0 is 1/2, right? So things kind of fall into place. So we end up with this relationship. If it's first order, this relationship for the half-life. So, first order, I don't want to make it too easy for you guys, but first order. So this is saying the same thing. We can actually rearrange this, the natural log of, let me fix that, right? We can, by that, so I absorb that negative sign into the natural log of the inverse of 2 basically by making that the natural log of 2. Ugh. Logs. I don't know if you follow that, but it's a log.
So this is first order.
First order, yep.
Is there
We are working on second. Yep, hold that thought. And it's probably the other half-life here.
well, I mean, like, are there going to be 3 half-lives? Like, is there 0 half-life?
Yeah, 0 half-life, you could, I'm not going to do it here, but it's an interesting thought, proof that I've actually included on a test before. And you can figure out any half-life if you do exactly what we did here. By recognizing T1/2, if it's a half-life, then your concentration of A is equal to half of your A0. And substitute away. Yep. So that's first, I'm gonna do for second. But one of the things, and actually I think I have it coming up written, the half-life, if it's first order, notice it doesn't depend upon the initial concentration of A. It's independent. And I don't care what you started with. It's got the same half-life. Okay. It's first order. Well, okay. So this is kind of what half-lives would look like. If you have, for instance, something that's 1 molar, and it goes to 0.5 molar, and it goes to 0.25 molar, 0.125 molar, you are having it all the way. It's becoming less and less concentrated. You can see the color changing. Notice that we have 6 hours to get 1/2, 6 hours to get half, 6 more hours to get half of that, 6 more hours to get half of that. Okay? There's a 6 hours difference between these snapshots. Okay? 6 hours to get half of that. So this is, if you were to graph it, kind of what it would look like. Along the x-axis, along the y-axis, we have concentration in terms of the thing we're tracking just happens to be a gas, so we're tracking it in terms of pressure. So the half-life here must be it's looking like 80 minutes. So if we go another 80 minutes, okay, or half of that, we go another 80 minutes for half of that. You get this kind of nice decay curve. So let's do the magic now. In substitutions like we did before, switching it up and looking second order. So here's one version of the integrated time concentration equation for second order. I'm kind of laughing when I look at this. To me, the second order, I'm like, dude, that's not much difference between those two, but that's okay. So we know to get a half-life equation, we need to go ahead and do some substitutions. For the A, we're going to substitute 1/2 A0, and then by definition, our time will be 1/2 T. So what does that look like? It looks like this. So now we have 1/1/2 A0 minus 1/A0 is equal to KT 1/2. Well, we can go ahead and take this guy and flip it up. So we have 2/A0 minus 1/A0. 2 minus 1 is 1. So we actually end up with 1/A0. Okay. So 1/A0 is equal to KT 1/2. Rearranging it to solve for your T 1/2, then your half-life is equal to 1 over your rate law constant times the initial concentration of your A second order. Okay, so it does depend upon the initial concentration of A. You need something like that?
Yeah, no, okay.
Just check. All right then, let's work a problem, I think. Oh, I should have looked at this one. So here's some tips. So one tip is make sure you know if it's first or second order. It'll either tell you, if it doesn't tell you, you can use the units of K, as long as it's only one reactant. If you're not given K, then actually you can find the half-life. If value K is not explicit. Oh yeah. So if K isn't given, okay, so say K is not given, then we can actually if we know a half-life, we can rearrange this to get K. Okay. If you were given, the initial concentrate, or just the, this was one that I mentioned a while back. I said, be careful, if it's first order, we have some kind of cool things going on here, where, for instance, the natural log of the ratio of A to A0, actually that could be a percent of what's remaining versus what you started with. So, for instance, I can't remember the numbers exactly, but if I were to choose some, if we, so if I started out with 0. I'll just go this, okay, and I was trying to find time when the concentration of A had decreased to half of that, 0.00500 moles. Okay, I could go ahead and take divided by, and you get, right? Are we good with that? So in other words, this is 0.5. So, in other words, I could just as easily said, find time when you have 50% of A remaining. So keep that in mind for first order. Okay. First and second's mixed up. All right. So yeah, we're going to do a few slides in part 5. Definitely won't finish part 5. That'd be cool. Okay. All right. Because like I said, I'm just paranoid. Activation energy. It's kind of the missing piece, or it adds to what we know about chemical reactions and how a reaction rate goes slow or goes fast. Activation energy. Going clear back to the beginning of talking about this subject, we said in order for reactants to go from reactants to products, okay, first the particles need to collide, then the particles need to actually have enough energy once they collide, and they actually need to be kind of like tail to tail or head to head sometimes. They have to be oriented properly. So with all this in mind, it's surprising anything ever gets done. Surprising any chemical reactions ever happen. So our rate is dependent upon all of these things. Will they find each other? Will they collide? Will they have enough energy? If they collide and have enough energy, will they be properly oriented? So, so if we go to rate, our rate law expression, rate for anything, we said is equal to rate law constant K times the molar concentration of A raised to its reaction order times the molar concentration of B raised to its reaction order. This right here, which we've been concentrating on, actually goes to this one right here, collision frequency. You know, that's directly related to the molar concentration. So I need something, and I'll go ahead and just do it on the same thing, with regard to sufficient energy and sufficient orientation. I just think it's such a beautiful science. These two things, I'm going to prove to you, are balled up in our rate law constant K. Of those three things, collision frequency is covered by molarity. Of those three things, energy and orientation needs to be balled up in your rate law constant K. Bottom line. Okay, so less dramatic is basically what's being said here. Your rate constant K needs to cover these two guys, just like I said. So what you're going to see here, and I'm amazed, I can't tell you how they figured this out, but we're going to actually take that rate law constant K, and this is again under the category of don't blame me, because we're going to use another variable, K naught. But we're going to break that down into parts. Parts is parts. So here you go. This is that rate law constant that we've all been working with, the rate law constant K. And I'm breaking it down into K naught and E raised to the negative EA over RT. Now, I don't know. I think I'm okay with open stacks, but honestly, for some, is that right? Did they do a little circle over it? Some textbooks call that the Arrhenius constant. A0, I think. Maybe totally butchered that, but I call it K naught. So, the rate law constant K really has this K0, K0, maybe better than K naught, sorry, K0, which covers the orientation, and then EA is a term we haven't run into before. That is your activation energy, so that's a big hairy deal. Of course, we run into R and a capital T. R is your ideal gas law constant, and T is temperature in units of Kelvin. Okay, so there's this. There's that. So if I go back and forth, how do I say this? This is unitless, and so that means that these units have to be equal to these units. So our orientation factor, K0, will have the same units as K. E raised to that power, that actually, those units that E is raised to that power, they need to all cancel. And they will cancel as long as temperature is in kelvins. We're going to go ahead and use the R value of that 8.3145 times 10 to the negative third kilojoules per mole Kelvin. And life will be just fine. All right. So orientation, what do we mean by orientation? Well, like I said, we saw a picture of it, or a video of it a while back. If you have two molecules that need to have certain ends facing each other in order to proceed from reactants to products, that is balled up in the K0. So our energy factor, E raised to the negative EA over RT, that actually then will say how many molecules, or the fraction of molecules that have enough energy to go ahead and overcome what we call the activation energy barrier to proceed from reactants to products. So activation energy. You're going to see it here in a minute on a energy curve. And it looks like this. We're used to looking at energy curves and identifying whether an overall reaction will release energy, we call it exothermic, or will require energy, we call that endothermic. We can get that from an energy diagram. Whether it's endo or exothermic, both energy diagrams will show this hump. So here we go. This is an example of an exothermic reaction. You're going to see reactants here, products here, energy is going to be released. So here we go. Initial, there's your barrier, okay, final. We know it's exothermic because the overall energy of our products is less than the energy of our reactants. So energy is released to the environment. So we can draw some lines here. I'm going to show you where your EA is, your activation energy. But before I do, this is your delta H that we talked about before. This is your change in energy from the reactants to products. Again, it will be negative, so it's exothermic. And that hump, my friends, is your activation energy. So it can have a lot of energy or not much energy. Okay, and actually how much energy it has will drive how quickly or how slowly the reaction occurs. Endothermic, you're going to have energy is put in, so that means that your products have more energy than your reactants. Okay, so that's an endothermic energy diagram. Again, to find the activation energy, we're going to draw our two lines. Identify our enthalpy change. We have a positive delta H. And all activation energies are endothermic, positive. So here is your activation energy for this endothermic reaction. I think that's a good place to stop. So we'll pick up here, take a running start at it on Wednesday.